Yeah, I mean, this is a lab. Maybe, yes. So, if you are following, if you are then you guys still please be quiet. Are we done? So, in case you are following, right, the combinational logic we just did right now does not store anything. As long as you give it an output, as long as you give it an input, you get an output. Once you change the input, the output changes. Like an AND gate, very, once you change the input, the output changes. Like, you don't store anything, right? Right? Yes. So now we are going to look at the memory element within your computing system. And I hope that you guys understand this already. So let's hurry it up and then we are done with the semester and then you guys can go and do it. Right, so what happens is that so now with this architecture here, right, from the scratch, from what I've told you, you guys can design an ALU from the scratch, right? You guys can design a multiplexer from the scratch. You can design all the components from the scratch. Now we are left with the memory, the register power, and the memory. So we're going to learn how to design register power and memory from the scratch. Then from there, it means that for the example, I can give you a very complex something. Give to the electrical guys. Right, so our first component, we are going to study the memory is register power. And then I hope that I won't go to the basic of the basic, like I know that you guys know what how to store one bit. You guys know how to store one bit using flip flops. Wow. All right, nice. So I'm making it as easy as possible. I won't go below that level. So, but you guys must know that there are components. You guys already know. I know that those doing computer know that we have what is known as a flip flop. Right? Flip flop. If you want to study the issue of flip flop, probably in first year or second year or something like that. Right? You know that. You guys know this already. I don't put that time to do it. But you know that we can cascade not gates to form flip flops to be able to store one bit. That's how we started. How to store one bit is very, very important, right? You can cascade two not gates. Right? So you have your input, you have your output. Right? So if here is one, what happens to this plate? And then what happens here? So you'll be able to store one bit within the system. Easy as that, right? So that's how memory started. Then we went to a company known as the D flip flop, where you have your clock, here, you have your D here, your data, right? And then you have your kill. So once the clock is high, your D gets sampled into the system, and then if the clock is low, your D gets stored. Easy as that. Easy stuff like that. Right? That's the history of memories, right? How to store just one bit. But we are going to see how to store more bits. Right? And our first component is the register power. Very, very important in any CPU. Any CPU at all you take has what is known as a register power. Right? A form of memory. Very, very small memory. Unlike your RAMs and then your DRAMs and then your SRAMs, right? Register power is also memory, but it's very, very small. within your CPU. Everybody knows that, right?
Yes, yes.
Alright. So in effect, I'll be giving you something like this. This architecture you have seen here is known as the input output of a register file. And what type of register file is this? This is a dual read port, single write port, 32 by 32 register file. Very important. Okay? Each word means something. Once you miss one word, you're putting everything wrong. So if I say, so pay attention. If you have, so I can give you only the word and ask you to draw the input of both architecture. And then as I said, once you get one word wrong, you are done. So why is it dual port? Dual read port. Study the architecture. This is just the input output. It's not even the internal architecture. It's just the input output ports. Right? Why do we say this is a dual read port? Two outputs. So we can read from two registers at the exact same time because we have QA and QB as the outputs. Have you seen it? Very important. Now we say this is a single write port. Why? You can write to only one port here, DW. Right? Right? Now it's a 32 by 32 register file. What do we mean by 32 by 32 register file? Master, why are you listening to your head like that? Now we have a 32 by 32 register file. That's what we say it is. So in the exam, I can give you anything. 4 by 8 register file, 4 by 2, 4 by whatever. Right? And ask you what is the meaning of that? That's the first question. So if I say this register file is 32 by 32, what do I mean? Anybody? Memory. How do you arrange memory? 32 by 32 register file. What does it mean? Higher. Mhm. Anybody else? 32 by 32 register file. Very important. If you don't understand it, then you get one wrong. One has to flip one for that. Like, because here is 32 by 32, probably it's easy. But if I give you 8 by 4, and then you flip them completely from 0. Right, so now, anytime I draw memory, I've been drawing this for the entire, how many weeks have you been here? I draw memory like this. Right? And then this actually how memory looks like on, on, on your machines, right? You have a number of locations. And I always say that each location stores some number of bits, and then we call that the what? Data weight. Data weight. Right? Then we have locations, right? And then those locations are known as the depth, right? Yeah. So a register file by the name just means that we have several registers within a file. It's like you have a file and then you have registers within it. Right? So these are the registers within a file. Right? So it means that automatically common sense will tell you that there must be a data weight and then there must be the number of registers within that file. Right? So here, 82 by 32 means that this second one is known as the data weight. Very important. If you miss it, everything you're doing is just chaff. Right? So here is the data map. So the data map is 32 bits. Right? Now we have the number of locations inside there is this. So it means that if I have a 32 by 32 register file, the data weight is what? 32. And then the number of registers within that file is 32. So from 0 to 31. Very important. Very easy and very right? Now the main thing is that I must know something. I must know how to address this. How many bits can I use to address each location? How many bits do I need? I've been doing this most of the time. 8. Yeah. We have 32 locations. How many bits do I need to address 32 locations? Simple as our question. Yeah? Hurry up. Wrong. So use that. If it is a obese, 32 will be there. Another answer. 4. If obese will be 4 there. 8. Another answer. Obese, 16. 8. 8 will be there. Last one. 64. It will be there. And then it's right up there above. And then last one. Look, it means that you guys are all quoting it wrong. I have 32 locations. I want to address it. How many people do I need? 5. Right? 2 to the power 5 is what? What is 2 to the power 5? Common sense. Okay, so you see how I said that you can actually get 100% or 0. And so and I should tell you that you're going with it. Once I say that I have 32 locations, how many people do I need to address? You must know that already. You must have some of these things that you can These are just common computer engineering stuff. You must know this particular things. I don't have to tell you that you need to the common something to know them. Okay, so this is the input output of a 32 by 32 register file. Now we have what is known as the data weight. Quick is here. Data weight, right? 32 bits. Why? Because this is 32 bits. Please pay attention. The output ports are also 32 bits. Why? Please here, as I tell you, you can actually get 0 or 100%. So if you don't understand anything, just say it. And I'm not joking, like, and I won't lie, and I can't even give you any marks for anything. Others, so I will just say, oh, what is the data weight of the QA? And if you say for your I can't even do anything about it. You guys must understand that. So either you're getting a very high mark or very low mark, and you guys are in folk here. You guys must understand what it means to pass or fail at this time. Right? Okay. So pay attention again. QA is 32 bits. Why? Common sense. Common sense. Each location stores 32 bits. So if I'm reading, how much can I read? 32 bits. Now we have what is known as to read, right? To write to a location. To write to each location. Right? I need what is known as the write address. Where am I writing to? As I said, and then we need 5 bits to address that. Pay attention. You need 5 bits to address that. And you must know that that 5 bits is not a random number. I got it from somewhere. I got it from because we have 32 locations. I need 5 bits to address that. So we have what is known as the write address. RW. 5 bits here. Very important. So to write to each location, I need this RW here, which is the write address. So I can go from 0 to 31. 0, 1, 2, 3. I can write to any of the location using this point here. I just give it the number, and then any data here will be written to that location. Do you get it? Yes, sir. Now, to also write, right, I need another signal known as the write enable. Only 1 bit. So to be able to actually write enable must be 1. Then I give it the address, then whatever data is here will be written to any of the locations that is specified by the write address, which is 5 bits. Right? Yes, now we have to be able to read, we will give Again, common sense tells us that we need an address to read from. So where are we reading from? We also need another 5 bits to address those 32 locations to read from. But here we have 2 read points. So we have what is known as read address A and read address B. I can read from 2 locations at the exact same time. So I need RA and RB, which are also 5 bits. As I said, this 5 bits is not a random number again. I got it from somewhere. So to read, I must give it RA a value here. RA must give it a value here, which can be from 0 to what? 31. Right? Because it's 5 bits. So once I give it RA and RB, the value stored within here will come to we have QA and then QB. So RA will give the data here, RB will give data here. Easy as that. Are you all there? Hope you understand. If you understand, just ask because the days is coming. As I said, you are actually getting this wrong or right. And probably if you get one of the questions wrong, all the others depend on that one. So 0. But you guys did digital systems, right? How were you taught digital systems? Like how were you taught? By some lecture or by drawing on the. Okay, so now that you have seen the input output ports, right? And then once I give you the 32 by 32, you know the data weight, the address weight, and all of that, right? That would be about 5% will be from that. So once we do that, now we now go to the internal architecture. What we just did was the input output ports. Input output, just input output. So what is inside there, right? So so, so your first thing is the D. The D is 32 bits. We are still dealing with our 32 by 32, right? So we have the 32 bit, and then we have register 0 up to what? Up to what? 31. Right? So we have 32 registers here. This D is connected to all of them. Right? The D is connected to all of them. But now, how do I write to one of the locations? I don't want to write to. Once I do something like this, I design something like this, right? When I put D here, right? The D is written to all the locations. From R0 to what? R32. If I give any value here, it's written to all the locations. But I don't want that, right? I want that it writes to one location at a time. So I must give it an address and stuff like that. So which component do I use here to be able to make sure that I'm writing to one location at a time? What? What? Huh? I can't hear you. 5 feedback to do. I mean, so far, the people answering questions, there's only one person, and that was the girl who was always sitting around here. So, for the rest for the class, so she's the only one getting the 5 marks. All of you is there. So now, start fighting for 95 marks. And those who don't also come to the class, and I use the attendance of each class to give about 25% of the marks. So if you didn't come for one, no how many marks you're losing. And go and fight for the rest. Right? So what component must I use here? A decoder. Easy as that. So pay attention that everything you have studied builds up. Everything I say from the past builds up to the present, right? So all we do is we need a decoder. And then you must know that because we are addressing 32 locations, we need a decoder with an output of 32. because we're addressing, as I said, for in the code we can only activate one line at a time. So they take two of them, and then I must know again how many bits do I need to address it. They take it to 5 bits. So that's why we have a 5 here. The right address. Are we are we all there? But again, we have another component. We have what is known as the right enable, as I said, from the input output. We saw the W right. It's known as the right enable. Before I can write to any location at all, my right enable must be 1. So from this circuit here, let's take it only this one. If right enable is 0, what happens here? You see that automatically here becomes 0. You cannot write to any of the locations as long as right enable is 0. You can only write when right enable is 1. Now, if right enable is 1, then you need an address. So let's say this is the first address, 0. So if yes, okay, let's say you have address 0001, right? So it means that the address starts from 0, 1, 2, 3 going, right? So if you have address 001, we are referring to here. So here will be activated. Have you seen it? And then if right enable is 1, then we are going to write to this register file. The D will be available to this register file. So that's how we write to the register file. Do you understand? So this is just writing to the register file. So now our next thing is we have the file again. Now we know how to write to it, right? From the front, right? We know that there's some circuit here that will be able to write to it. Now we should know how to read from it, right? And there are 32 locations. We know that already. Yeah. 32 locations to read from. Now, and then we have 2 ports, QA and QB, right? So only one of these 32 locations can be routed to the one of the ports. So let's start with QA, right? Just one of the ports. We have 32 lines here. What components can I use to route all of this one and then it goes to one? Multiplexer, right? So everything we have studied in the past comes here, right? So we use a multiplexer, very, very easy. But again, a very important component in the multiplexer is that we need to be able to select. So which lines are we routing? And then what is the number of bits used to route those lines? Right? So we have the RA, which is the read address A, 5 bits, important. 5 bits, it used to route the 32 of them. So once we give it an address here, let's say we give it address 0001, so address 1. Only this one will be routed to the output. Right? And then the output again is 32 bits, as easy as that. But here we have 2 of them. We have QA and what? QB. So how do we design a dual read port? What must we do here to make sure that we have QA and QB? Anybody? So here we have done for only QA. How do I adjust this circuit to make sure that I have both QA and QB? Very easy. So I tap all the lines, give it another multiplexer, give it another RB, and then I have my dual read ports. So I tap all of here, put it to another multiplexer. So now here I can read from two locations of the register file at the exact same time by giving it RA, the address RA, and address RB. You understand? So you see that everything we have studied in the past come to out of this. So this is the entire architecture. Here is how we read. Here is how we write to it. Here is how we read from it. Simple like that. So this is the internal architecture of a register file. If you're not seeing one before, this is how it looks like. Are we all there? And then this internal architecture is for a 32 by 32 register file. So I can give you a 32, a very simple one, a 32 by or an 8 by 4 register file, and I want you to draw the internal architecture for like 10 marks or something like that. 10 marks. Something like that. Any question? So as you see, the register files are just very simple to design, right? And then they are very fast. The way they design makes it very fast. Right? Yeah. And then we can easily add, so here we can easily add ports to it. If I want to read from 4 ports, all I have to do is add 2 more what multiplexers, and I'll be able to. It's very easy to add them. But here the issue is that we cannot store large quantities of data in the register file, right? Yeah. Because once you are storing large quantities of data, means that you are using very huge decoders and huge multiplexers and stuff like that, right? So if I have something like this, if I have a 32 megabyte register file, what do you think is the address line? How many address lines are there? Very easy. This is one of the questions also. So I have a 32 megabit register file. How many address lines are there? 32. And then how do I even go about calculating it? How do I calculate it? 32 megabits. Okay, I will leave it for the exams. Right. So, but you must know that using those kind of decoders and multipliers results in a lot of gates. That's what I was saying. So, and then I must also know how many logic gates there are and then how many transistors there are. When I give you a circuit like that, right? Like for instance, if I give you something like this is an 8-to-1 multiplexer, right? 8-to-1 multiplexer. I can ask you how many logic gates are within this 8-to-1 multiplexer. And you must give me an answer. So, how many logic gates do you think there are there? Huh? What? 9 logic gates. Okay. And I'll leave it to you in the exam. So, if it's 9, okay. How many logic gates are within this? 2 logic gates. These are all logic gates, right? This is one logic gate, right? All of these are logic gates. This is a NOT gate. Not. So I need to be able to count all of them. So how many are there? Now again, I need to know the number of transistors within this. How many transistors are within one AND gate? One input, a 2-input AND gate. Who knows? You have done this already. 2-input AND gate. How many transistors are here? Even a very simple one. How many transistors are within a NOT gate? How many transistors are within a NOT gate and inverter? You have done this already. Okay, I'll leave it to you there. I'm not going to repeat myself again. And I thought about it, they even spent time drawing the PMOS, NMOS, we did all of this, and then you guys don't know how many transistors are within a simple inverter. Alright, so we have seen how to draw the register file, right? Now we And then, as I said, the register file stores very, very little information, very, very small, right? We need a way to store more. That's where we use the actual memories. And then how are they designed, right? So here we have what is known as the same way like the register file. We have this architecture here. Then this is known as, again, the input output port of memory. And then this memory is known as the SRAM. You guys know what that means, right? The static random access memory. Right? This is how it looks like. We have a port for the address. We have a port for the address. We have a port for data. Right? And then as you can see here, the address is only an input port, right? But the data is a kind of dual port. Not dual port, I mean bidirectional. Right? You can write, you can read from here, you can write to here. So if I want to write to this memory, right, I give it an address, and put the data on this line, and then it will go to the memory. In case I want to read again, I give it an address, and then the data will come out of this bidirectional line here. Right? Now, the most important thing is that how many address spaces are necessary for a 4M by 8 SRAM? Another question. So I have a 4M by 8 SRAM. How many address spaces are here? How do I calculate the address bits? So now, as I said, we need to know, once I give you something like this, a 4M by 8 SRAM, right? I need to know the data weight. I need to know the address weights. Very, very important. So if a 4M by 8 SRAM, what is the data weight? Hmm? I mean, you guys buy RAMs all the time, right? You see that they write stuff like this on the RAMs, right? Your RAM that you buy for your PC, they write stuff like this on it. 4M by 8 SRAM. You must know what that means. You must know that this is how it's arranged. You must know the data weight. You must know how many addresses are there or how many locations are there and stuff like that. So if I have a 4M, this is a 4M by 8 SRAM. What is the address range? Oh, hurry up, hurry up, hurry up. What is the address range? Hmm? 8, yes. Why? Because we use the last number to identify the data weight the same way, like this. We draw it like this, the application. So we use the last one to know the data weight. Data weight, right? Now, how many locations are there? 4. 4 locations. We have a 4M by 8 echelon. Don't just see the M as so what David, what do you think this M is? Hmm? Yeah. 4 million of them. Yes. So but in digital systems we don't use million, right? So how many locations are there? And how do I calculate it? Oh, hurry up, hurry up, hurry up. How many locations? I mean, you guys buy round all the time. You guys see these numbers all the time. What do they mean? 4M, 4M. So in computing we have KM, giga, kilo, mega, giga, right? In in your normal kind of number, K is 10 to the power 3, M is 10 to the power 1, and then G is 10 to the power 1. Now, somebody said that. In computing, right? K is 2 to the power what? 2 to the power 20, 2 to the power 30. This is what we use in computing. It's not your millions and then thousands. We are using the 2 because we are dealing with bits. Understand that? Hmm? You said it was like bits, ones and zeros, so 2 to the power something. That's why only ones and zeros. Right, so now here we have 4m by 8. So as I said, the 8 is the data width. Now I need the number of locations. How many locations are there? So all I do is 4m. M is 2 to the power what? 20. Times 4 is what? 2 to the power 2. So my total number of locations is 2 to the power 22. Now 2 to the power 22 locations. Very important. Now, out of these 2 to the power 22 locations, I need a way to address each location. How many bits do I use to address those locations? 22. Simple, right? So you have seen that I can just give you just one line, just 4m by 8. I can ask you about 3 or 4 questions from it. What is the data width? 8. Right? How many locations are within the 4m by 8? 2 to the power 22 locations. How many address lines do I need to address 2 to the power 22 locations? 22. Easy. Right? So 100% or 0%, as I said. Now, so this is a 4m. This is 4m by 8. We have your address line again. You must know what the address line is. The D in, the D out. So if what is the D out? How many bits are the D out? What is D out? D out, data out. We have data in data out. How many bits is data in and how many bits is data out? So data in is 8 bits. Data out is what? 8 bits. It's in the question here, so you don't just guess it. I mean, 100% or 0%, as I said. It's well, Alright, so our next step. So here, to read or write to S to read or write to SRAM, there's a very important signal known as the chip select. The chip select must be 1 before I can read or write to any SRAM. So our chip select must be 1. If the chip select is 0, I cannot read or write to any SRAM. We also have what is known as the write enable. So to write to a location, like how we did for the other one, right? We need a write enable. We also have what is known as the out enable. To read from the SRAM, we need what is known as the out enable. If the out enable is 0, you can never read from it. The out enable is 1. That's when you can read. Give the output, so to read from it, give an output enable of 1, then give your address, and then that value from that location will be made available to the output. Right? Yeah. Yeah, the chip select must be on before you can read or write. Once it's 0, no operation can be done. Read or write cannot be done at all. If it's 1, it means that you are ready to read or write. If it's 0, once the chip select is 0, whether the write enable is 1 or it doesn't care anymore. It must be on. Okay, it's like you are turning the chip on, right? Okay, so these are the questions. So you'll see 8 here. I'll ask the values here 8, 8, 32, and stuff like that. And then another simple one. How do you design a 4 by 2 memory model? Right? Very, very, very interesting stuff. So the 4 by 2 means that Uh, what is the data weight of a 4 by 2 memory model? 2. So that's why we have D1, D1, D2 here. 2, very important. Now, how many locations are there within a 4 by 2 extra? 4 locations. How many bits do I need to address those 4 locations? 2. That's why you have 2 here. So you see how easy it is. Right? And then we have our output, right enable, output enable, and all that easy stuff. Easy stuff. This is the internal architecture of the 4. Very easy. This is the internal architecture of a 4 by 2 memory model. Right? So very easy. Again, don't be scared about this thing at all. So pay attention. So let's say just look at it very well. We have 2 to 4 decoder for my addressing. In case I want to write to any of the location, right? I have to give it an address here, and one of the lines here, either 0, 1, 2, or 3 line, will be selected. I know that already, right? I'm using a 2 to 4 decoder. So let's say I want to write to memory location 1. So 0, pay attention, 0, 1. I give this address 0, 1 here. Power pin to this line. If I give 0, 1 here, what happens to this line? Will it be 1 or 0? Look on the slide of the value. Here will be what? 0. 2 will be what? Pay attention. 0. 3 will be what? 0. The only line that will be active is what? 1. Now, as long as here is 1, I need another signal known as the right enable. Have you seen the right? Just steady it and see and trace it. You see, right enable is here. Right enable goes here. Have you seen it? Yes. Right enable goes here. So it means that if 1 is at I mean, you guys really excellent. Just see, very don't, as I said, once in data system, don't think far at all. It's just ones and zeros. Once you make up your mind that you don't understand, you never understand, you're going to get a zero. Right? But once you make up your mind, please pay attention. Once you make up your mind that we don't have to read a lot on, and then as I was saying, this is not a reading course. Right? Once you are reading, it means that you are going to get zero. Once you don't understand from the class, you are going to get zero. Zero or nothing. Once you don't understand from the class, just don't come to the exam so you can ask any guys. But why I'm saying that is that very easy to trace. Just trace. Yeah, signals. We have inputs. We have outputs of signals. You know that we have zeros and ones. We have logic gates within there. You know the two table of an AND gate. Very easy. Once you know all this in your head, this is just very easy. You can easily understand it. So how do I write to this memory? I want to write to memory location 1. Once I have a 2 to 4 decoder, I can address 4 locations. So memory location 0, 1, 2, 3. Right? So once I give it memory location 1, it means that this is the line that will be active. Right? We have a signal known as right enable. Once the right enable is 1, it's the only time I can write to it because it's an AND gate. Once right enable is 0, you know that for an AND gate, once one of the input is 0, the output is 0. Right? So if I have 1, this line is active. Right? I have just trace it. My right enable line is here. Right enable line comes here. If it is 1, it means that, and this is also 1. that's when that's when these components here are enabled. Have you seen it? Enable here. It will be enabled, and then I can put my data here, and it will return to that location. As easy as that. If you don't understand, I can't break it any further. Right? So we have what is known as the web lines. As you can see, the 0, 1, 2 are the web lines, and then we have what is known as the bit lines. So this is where the data comes out of. The data comes out of the bit lines. So go and study how to read from it. You let me ask you. Who can trace and show me how to read from memory location 3? If let's say there's a value in memory location 3, how do I trace and see how I'm reading from it? Try. Am I pointing to? Am I pointing to somebody? Right. So I want to read. There is a value in memory location 3. So how do you think I can read from that location? And I want you to understand. Once you're able to explain this, you don't have to fix it. Then you're quick. So just start tracing. So start tracing. To read from this line, right? I need an address. That's the first thing. The address line must be distributed. And where is the address line? You see the address line there. So I said memory location 1. I said, be facing to me here. So I'm ready for memory location 3. So mean that my address should be 3. And then one address is 3, that line is active. Now I have a signal known as the output enable. Have you seen it? Yes. So if the output enable is 0, and then my 3 is 1, how happens? Trace. If this one is 0, if it's 0, and then the output enable is 1, what happens? So it will come in, it will tell me. This one will okay, so the line 3 is on. Line 3 is 1. Output enable is 0. What happens? Trace it, let me see. Why? It should be 0, right? So it means that nothing will happen. But if my line 3 is on, my line 3 is 1, and then my output enable is 1, what happens? So it took 1 part. It says 1. Yeah, so you can trace that to enable the D flip-flop there, and then the value, if there's any value within the D flip-flop, it will come out of the D0, D01, and the D out 1 and the D out 2, as easy as that, right? Any question? Any question? The last one, but my battery is running low. I don't want to come in this week. So, charger. So now, I can combine to construct memory. To construct memory, right? I can combine several smaller memories to form a bigger memory. You guys know that already, right? So now, one of the questions that carries a lot of maths, about I think 50 maths. This. Okay, so now I have everybody should solve it. I have a 4K by 1024 SRAM, right? 4K by 1024 SRAM. That is a smaller memory. I want to construct 4M by 8 SRAM from 4K by 1024 SRAM. How many of the 4K by 1024 SRAM do I need to construct a 4M by 1024? A 4M by 8 SRAM. Thanks a lot. Okay, so hurry up and let's go. What I have is this. What I have is this. I have a memory. I have a larger memory, right? Which is 4M. You know M is mega by 8 SRAM. And then I want to construct this memory. I don't have this memory yet. This is the memory I want to construct. I have 4K by 1024 SRAM. So, and I won't answer this question, but I'll just be for you them if I'm going and find answers to them or not. When I take my 4K by 1024 SRAM, right? What is the data weight? What is the input? What is the input weight? The output weight? What is the number of locations within the 4K by 1024 SRAM? How many bits do I need to address those locations? About 5 months. The second question: I have my 4M by 8 SRAM, right? What is the data weight? The input data weight, output data weight. How many locations are within the 4M by 8 SRAM? Then, how many bits do I use to address the 4M by 8 SRAM? So that's about 5 months. 5 months, 5 months, 10 months. Now, how many of the 4K by 1024 SRAM do I need to construct the 4M by 8 SRAM? 15 months. Then, show working. The last one. Yeah, I said, after all those questions, listen, from here, you'll get five questions from here, one mark. 5 questions from here, one mark. 10 marks. For the 5 marks, how many 4K by 1024 SRAM do I need to construct a 4M by 8 SRAM? How many are there? 5 marks. So working. Once you write the answer, you won't get a mark. I want you to show me how you got the answer. Master, this is a very simple question that will show that the SS you went to is good or not. If you can answer this question, then you have to go and close down your SS. I have a small memory. I want to construct a big memory. I know the exact number of the memory I have. 5. How easy can this one get? Who has the answer? Who has the answer? 8. Simple. 5 marks. Show working. Let them show working. How can you show working? So the 8 just from defined intervention. Open AI. Right. So what you do is this. Simple. So these are which will you use? Which will you use? What? So pay attention here. Very, very simple. So I have 4m right by 8. All I do is I divide it by what? 4k by 1024. Right? And if I do that, what do I get? 4m, pay attention. 4m is what? 2 to the power 2 times 2 to the power 20 times 2 to the power 3 divided by 4k is what? 2 to the power 2 times 2 to the power 10 times 2 to the power 10. So here I get 2 to the power what? This plus this plus is what? 2 to the power 25. Divided by 2 to the power what? 22. 2 to the power what? 3. 8. 5 marks. Done.